Good morning everyone, welcome back. Today we're gonna continue with the Vulkan tutorial. In this case we are on the Vertex buffers chapter. So let's get straight into it. Let me run the program first to know the current status. So yeah, I remember we had a crash and it was due to the fact that we are doing this. So here you can see the result from the previous streams. We just have the triangle, but if we go to our Vertex shader, you will see that we have the vertex positions and the colors hard-coded in the Vertex shader itself. So in this chapter we're gonna see how we can create a vertex buffer so we can stop hard-coding these values. So let me go back and commit these changes. Get physical. Push this and let's start reading this chapter. So in the next few chapters we're going to replace the hard-coded vertex data in the vertex shader with a vertex buffer in memory. We'll start with the easier approach of creating CPU visible buffer and using memcopy to copy the vertex data into it directly. And after that, we'll see how to use a staging buffer to copy the vertex data to high performance memory. First, change the vertex shader to no longer include the vertex data in the shader code itself. So we can get rid of these hard-coded values I was mentioning, like so. And we can add two input locations. Location 0 is gonna be the position with 2 coordinates, and location 1 is gonna be the color. Then here we can replace this with in position, and we can replace this with the color that comes in, like so. Yeah. So in position and in color are vertex attributes that are specified per vertex in the vertex buffer. Just like we manually specified a position and color per vertex using 2 arrays, make sure to recompile the vertex shader. Just like frag color, the layout location X annotation assigns indices to the inputs that we can later use to reference them. It is important to know that some types like dvec3, 64-bit vectors, use multiple slots. That means that the index after it must be at least 2 higher. I see. Vertex data. We are moving the vertex data from the shader code to an array in the code of our program. Start by including the GLM library, which provides, okay, we're not gonna use the GLM library. And by the way, we need to recompile the shader, so compile. We have this script which simply invokes glslc to compile the shaders. Then now we can define a structure to hold our vertex data. So maybe we can add it up here before main. Struct vertex. I'm gonna make it compatible with C, so in case the layout matters, we don't get any issue. Then for the position, we are gonna use slices for now, tuples, so we don't have to import any library or create our own vector2 and vector3 structs. So we're just gonna use a tuple with 2 elements, floating point for the position, and a 3-element tuple for the color. Like this. Okay, after that we can specify our vertices. Where shall I put this? I'm gonna put it as a constant for now, but I may change this later. And it is a vector, so probably we won't be able to, because vector allocates, we won't be able to do it as a constant. We can do it here. Vertices is gonna be a vector of vertex, and we can use the back macro to specify then position for the first one is gonna be 0.0 minus 0.5, and the color is gonna be 1.0, 0, and 0. That's the first vertex. Now we can copy this one a couple of times and just change the necessary values. So this one, 0.5, 0.5. The color can be green. This one, the color is gonna be blue. Oops. And the position is 0.5 minus 0.5, 0.5. I think I got that correctly. Binding descriptions. The next step is to tell Vulkan how to pass this data format to the Vertex shader once it's been uploaded into GPU memory. There are two types of structures needed to convey this information. The first one is BK Vertex input binding description, and we'll add a member function to the Vertex struct to populate it with the right data. Alright, so we could do something similar here. We could add an impl block for Vertex, and then add this function get binding description as an fn, and it doesn't take self because here they are declaring as a static function, but it returns the BK Vertex input binding description. So we can probably just return bk vertex binding vertex input binding description, but we are gonna require all the fields that this has. So let's grab it from our bindings. Okay, vertex input, yeah, it's here. It takes the binding, the straight, and the input rate. So like this. And down here they show us how to fill this. The binding is gonna be 0 for the first attribute at least. Then the stride is just gonna be the size of the vertex. I think in Rust we have std memory, maybe? Size of? Yeah. Size of, which takes a type parameter. And I think we can use self. And we need to cast this as a U32. Do I have std? Use std memory. I'm gonna import that, and then we can simplify this. You don't need to name std. Finally, the input rate, we're gonna specify it as input rate vertex. And not sure if we have this constant defined. Looks like we do. Yeah, we get a bunch of warnings. But that's okay. We will fix them later, I guess. So good, we have this get binding description ready for use. And here it says what all of these fields mean. All of our per vertex data is packed together in one array, so we are only going to have one binding. Okay. The binding parameter specifies the index of the binding in the array of bindings. The stride parameter specifies the number of bytes from one entry to the next, and the input rate parameter can have one of the following values: input rate vertex or instance. So we move to the next data entry after each vertex, or move to the next data entry after each instance. Since we're not using instance rendering, we'll stick to per vertex data. Makes sense. Then the second structure that describes how to handle vertex input is bk vertex input attribute description. We're gonna add another helper function to vertex to fill in these structs. So we do something similar here. We can have a get attribute descriptions. Here they are returning an array of 2 elements. So in our case, we could return also an array of 2. Let's do what they are doing for now, and we might change it later on. So, oops. So this should be the return type, an array of 2 bk vertex input attribute descriptions. And here we just return the array vertex input attribute description. This is the first one, and we need another one. And these ones are gonna have some fields. In here, we're gonna have the binding, the location, the format. In the format, we specify how many components each of the attributes has. And the offset, the first one is gonna be 0. And the second one, what are you complaining about? This needs to be a semicolon. So basically, in our shader, these are the two attributes that we have. One is the position, which is at location 0, and one is the color, which is at location 1. One is a vector 2, the other is a vector 3. So that's what we are defining right now. We have two attributes. The first one is at location 0, and it has an R and G floating point components. The second one is at location 1 and should have RG and B32, I'm guessing. And we also need to deal with the offset. So yes, here they are specifying the different types that we can have for the format. The binding specifies which binding. We only have one binding with index 0, so we're gonna use 0 for both of them. And then I need to look up if there is something similar to the offset of operator in Rust. Because I've never used it before. I would like something from the standard library, not I don't want to use any crate for this. Rust standard mem, maybe? Standard mem. Align off. We were using size off before. Maybe in FFI or in core. No, here we just have sometimes pointer offset. No, this one is for increasing pointers. offset off, doesn't look like intrinsics. And this is nightly. So, well, for now, we're gonna hard code them. We know that the first field will start at offset 0, because this is a C-like structure, so it will have that same layout. And for the second one, it should be standard memory size of needs to be passed as a U32. And I want to basically print this out. And just exit after that. What's the problem here? Vertex input attribute description cannot be formatted, so we need to derive it for this type. So in fact, I'm gonna derive it for both debug, for this one and this one. Then I think we should be good. So if we now run this, cargo run, we need also to derive it for PK vertex input rate. And let me pretty print it so we can see it more clear. So the first attribute starts at offset 0 and the second one starts at offset 8, which I think makes sense because each float is 4 bytes, like 32 bits is 4 bytes, so 4 plus 4, it's 8. So color should start at offset 8. One more thing I want to verify quickly is size of vertex. So the total size of vertex is this is 8 and this is 12. So there is no padding in between, which is what I wanted to know, because size returns 20, which is just these two fields added. Okay, good. Now we can get rid of this stuff. We don't need it anymore, and we can proceed with the tutorial. So we now need to set up the graphics pipeline to accept Vertex data in this format by referencing the structures in Create Graphics Pipeline. So if we now go to Create Graphics Pipeline, and we find the Vertex input info. First we were creating the shader modules, and next have the creation info. Yeah, Vertex input state. Vertex binding description and Vertex attribute description count. So here they are hard coding basically the sizes, and I'm gonna do the same. So the first one was Vertex get binding description, which returns one Vertex binding. So, and we need it to be a pointer, so we can just get a reference to it. And the second one, either we call this twice, get attribute descriptions, and get the length of it as a F32, or we hard code it as 2. And we need to call it again. Vertex get attribute descriptions as pointer. Yeah, we have this method on array, so let's see if that works, if that compiles at least. I will check, and it does. We're still getting a few warnings, but that's okay. But I'm guessing that if we run this now, we're gonna run into trouble. Yeah, because we get a bunch of validation errors and our triangle has stopped being displayed. So we'll need to fix that on the next chapters. So, Vertex buffer creation. Buffers in Vulkan are regions of memory used to store arbitrary data that can be read by the graphics card. They can be used to store Vertex data, which we'll do in this chapter, but they can also be used for many other purposes that we'll explore in future chapters. Unlike the Vulkan objects we've been dealing with so far, buffers do not automatically allocate memory for themselves. The work from the previous chapter has shown that the Vulkan API puts the programmer in control of almost everything, and memory management is one of those things. Buffer creation. Create a new function, create Vertex buffer, and call it from init Vulkan right before create command buffers. So I'm not sure we had a create command buffers. We were doing it right in line. So bk create command pool. Here we're creating the pool and the command buffers. So, and they say to create the Vertex buffers right before the command buffers. So basically here. And let's see how they create them. they create the BK buffer, create info, and ultimately they call this BK create buffer, which can fail, so we need to wrap it in a check macro, which basically panics if we don't return BK success. And this takes the device and this BK buffer create info, null pointer for the allocation callbacks, and gives back a vertex buffer, which we need to pre-declare. Vertex buffer, which can be initialized to a null pointer. So for the creation info, we need, what do we need? I'm guessing we're gonna need S-type. Yeah, S-type. And let's see if we have, do we have this function in our bindings? Create buffer? No, we don't. So let's go ahead and add it. We can add it, where do we add it? Here after, no, maybe after allocate command buffers. Pub-fn, BK, create buffer, takes in the device, the create info, BK buffer, create info, which we're gonna need to add in, takes in the allocator, and gives back a P buffer. And returns a BK result. So something like this. Let me open the Vulkan header so we can verify that I did not make a mistake. So here it is, we take the device, the create info, allocator, and we give back a buffer. So now we need to find out this BK buffer create info. Can grab it, and we need to put it somewhere. So I want to put it also closer to after the command buffer related structures and before the semaphore, so that would be here. The order doesn't matter so much, but it's just for me to easily find out where things are. So now we need to convert this into a proper Rust structure. And I'm gonna record a macro, quick macro. So public, then delete this. And then go to the next line and stop recording. It doesn't work so well but doesn't matter. Now I just need to fix the ones that have pointers. Const cvoid, and this one, pub, delete, oops, delete, and it was a public const u32 pointer. So I think I got that right. And now we need to introduce these two. This should be A32. And now we just have these two errors. We need BK buffer create flags and BK buffer usage flags. So if we go to where we have our flags defined, we can add two more type definitions. BK buffer create flags is equal to BK flags and BK buffer usage flags. I think that should be everything we need, and now we just need to fill it in. Pnext is gonna be null pointer. Flags, they don't specify anything. Size is gonna be the size of our vertex structure multiplied by the amount of vertices we have. So vertices.len, and it should be specified as VK device size. So I'm not sure if we need to cast this. Then we need the usage, which is gonna be vertex buffer, and the sharing mode exclusive. And what about the Q family index count and the Q family indices? They don't seem to be using them, so I guess we can set them to 0. So family index count is gonna be 0, and PQ family indices can be null pointer. So here it complains that this should be U64, so we can cast it to BK device size. Then we cannot find BK buffer usage vertex buffer bit. So we can grab all of these constants and add it to our list of constants. So down here we have a bunch of constants. We can add it to the bottom of all of them. Down here. And we're gonna need to format this. So basically pub const BK flags, go to the end and replace with a semicolon and go to the next line. Repeat this a bunch of times. And now we are good. What else do we need? Here this should be a colon. And here I missed a nail. And I think that should be all. So we now should have a vertex buffer, which is created after the command pull. So in our cleanup code, we can go ahead and destroy the buffer. The buffer should be available for use in rendering commands until the end of the program, and it does not depend on the swap change, so we'll clean it up in the original cleanup function. I think we can destroy it before the swap chain, so we maintain the stack order. So let's see if I'm right. Okay, destroy buffer, taking the device, the vertex buffer, and move. And of course we're gonna need to add the binding for it. Destroy buffer, taking the device, the buffer, and the allocator. Let's make sure that it doesn't return anything. We return void, so yeah. So now we should, well, we're still gonna have all the warnings, all the validation errors, because we're still missing to connect some stuff, but I think we're cleaning up properly. The buffer has been created, but it doesn't actually have any memory assigned to it yet. The first step of allocating memory for the buffer is to query its memory requirements using the aptly named bk-getBuffer memory requirements. Okay. So right after we create the buffer, we can have these mem requirements. Not sure what it's gonna be. Maybe we can set it to default and derive it later. And then we call bk-getBuffer memory requirements. Takes the device, the vertex buffer, and writes into the mem requirements. And it does return void, so no need to check for errors here. Let's go ahead and add it to our bindings. bk after destroy buffer, maybe bk pubfn get buffer memory requirements, takes the device, the buffer, and it returns the memory requirements. Mute pk memory requirements. And I want to see now what this is. pk memory requirements. It's just a simple struct. So let's go ahead and add it after pk buffer create info. Down here. Takes in the size. The alignment and the memory type bits. So all of these I think implement default, so we can probably just derive default. Is it so? Have a check. Yeah, it compiles. And what are the fields? The size of the required amount of memory in bytes might differ from pk buffer info size. Alignment, the offset of bytes where the buffer begins in the allocated region of memory. Depends on buffer info usage and buffer info flags. Memory type bits, bit field of the memory types that are suitable for the buffer. Graphics cards can offer different. Let's do one more thing. Let's derive debug, and we can just print out the memory requirements. pk get or pk memory requirements for Vertex buffer. I'm just gonna crash right after that. Or maybe to, because otherwise we're gonna see all the validation errors because we're still not done. Cargo run. So the size is 60, the alignment 16, and the memory type bits is 1. And something else that I want to see is this size. So before creating the buffer, I'm gonna print also creating vertex buffer of size that. So we can compare the. Okay, in our case, the two sizes seem to be matching, but we get an alignment of 16 bytes. Yeah. The offset in bytes where the buffer begins in the allocated region of memory. Is it the alignment? Thank you for the follow, Mighty Core. How are you doing? So, well, let's continue reading and see. So, graphic cards can offer different types of memory to allocate from. Each type of memory varies in terms of allowed operations and performance characteristics. We need to combine the requirements of the buffer and our own application requirements to find the right type of memory to use. Let's create a new function, find memory type, for this purpose. You are a game dev noob. Me too, man. You don't know what a Vertex buffer are. Well, I was at your position not so long ago, so yeah. You just need to read a little bit about it and you will get it. It's not very complicated. A Vertex buffer basically is where allocation in memory, usually on the GPU, where the Vertex data is stored. So the vertices for your models basically go into Vertex buffers. And right now we are seeing how to create them in Vulkan and how to allocate memory for them and fill them in later on. So yeah, that's what we are doing. Yeah, no problem. Let me know if you have any other question. I'm happy to answer that. So let's see, we need to create this function to find the appropriate memory type. So let's put it maybe at the bottom, somewhere here. So function find memory type, which takes a type filter and also some memory properties. And we give back U32. And let's see how do we do this. First, we need to query info about the available types of memory using pk get physical device memory properties. Okay, so probably we are going to have to pass the physical device as well. And now we are ready to query the memory properties. Let mem properties should be device memory properties default probably, and then we can call this function, passing in the physical device and the main properties. Do we have, yeah, we need to add this function to our bindings, basically. So bk get physical, okay. So in our list, we can add it after pk, maybe close to the buffer functions. Yeah, down here. pk get physical device memory properties. Takes in the physical device. Returns a pointer to the memory properties. not sure if we have this type defined already. Looks like we don't. So we need to also add it. This is the device memory properties 2. We need the 1. This one. So let's add it at the bottom of maybe in memory requirements. Yeah, let's add it after this one. Make it public and convert it to Rust format. This should be U32, and public. This one should also be public, and it's an array of BK memory type of size, BK max memory types. This one is just a U32, and finally the memory heap. It's just an array of BK memory heap. I'm not copying. No. And I think these need to be semicolons, not columns. So I think I got that right. Let's check if compiles, probably not. Cannot find BK memory type in the scope, so yeah, we need to add this type also. BK memory type, where is it defined? Is another structure. It just has some property flags and a heap index. Property flags and heap index as a U32. Now what? We need to define BK memory property flags, right? So copy this and let's add it with the rest of our flags. Now I think the only thing missing is this constant BK max memory types. So it should be basically the size of these arrays, which is 32. Right. So here we have some other sizes, so we can add it here. Const BK max memory types should be a U size, since we're using it to define the size of an array, and it's 32. we already have extension name size and description name size and device. Let's move this to the bottom to keep the same order. Memory types. Let's add also, since we are modifying this, match memory heaps. We might need it in the future, so it doesn't hurt to add it now. Memory types, heaps, physical device, extension name size, description size. And well, the rest we don't need it, so we keep it like this for now. VK memory heap. So we also need that type. We defined the memory type, which is used in here, but we also need the VK memory heap. Which is just a size and some flags. So simple enough. Abstract, VK memory heap. Takes in size and flags. And we're gonna need to define these flags. I'm not wrong. Yeah. We're still getting some errors, but now we get errors on main, so we are doing progress. We're making progress. So yeah, we were calling default on VK physical device memory properties. So we need to derive it. In here, derive default. Not sure if it's gonna work because we have these arrays. And also this type should derive also default. Find memory type implicitly returns empty the unit as its body has no tail or return expression. That's fine. Let's go to main. The problem is that this function still doesn't return U32, so let's try to fix that. After querying the physical device memory properties, which returns two arrays of memory types and memory heaps, we need to find a memory type that is suitable for the buffer itself. So the way we do it is we basically iterate over all the memory types. So we have a for I in 0 up to mem properties memory type count. We check if the type filter that was passed in, type filter, and one shifted by I bits is not equal to 0, because this needs to be a Boolean expression in order to be inside the if condition. But we'll see that. Then we just return I as a U32. Otherwise, this should be unreachable, or maybe panic fail to find suitable memory type. And what are we complaining about? Yeah, what I was saying. Expected bool found I32 because the AND binary operation returns a U32, so we need to tell it to not be 0 in order to have a boolean. And maybe we need more parentheses, or maybe not. And what's the problem? Up here, call to unsafe function, that's right. We need to wrap this on an unsafe block. Very unsafe. Very unsafe Rust. I will check this. Cannot borrow main properties as mutable as it's not declared mutable. So let's just declare this as mutable. And now we don't get any compile errors. So let's continue reading through this. The type filter parameter will be used to specify the bit field of memory types that are suitable. That means that we can find the index of a suitable memory type by simply iterating over them and checking if the corresponding bit is set to 1. However, we're just not interested in a memory type that is suitable for the vertex buffer. We also need to be able to write our vertex data to that memory. The memory types array consists of BK memory type. The properties define special features of the memory, like being able to map it so we can write it to it from the CPU. This property is indicated with the BK memory property host visible, but we also need the BK memory property host coherent bit. We'll see why we need when we map the memory. So apart from checking this, we also check that mem properties dot memory types at index I dot property flags and the properties that were passed in is equal to properties. Why is it treating I as an I32? As a U32, sorry. Is it because here we're shifting and then adding with type filter? Anyway, we can force it to be use size. And now it compiles. So I think that finally we have defined this. So Can I get rid of this then? If I is an I32, looks like we can. Yeah, looks like we can. So now we can allocate memory for our buffer. So right after creating our buffer and getting the memory requirements, we can have this Vertex buffer memory. And then we can call bk allocate memory for this device, passing in a structure bk memory allocate info. And we also need null pointer, and we write into the Vertex buffer memory. And here we need the S-type and probably more stuff. So here we have the function. We take the device, the allocate info, the allocator, and we return the device memory. We just need to define the allocate info somewhere. Maybe down here. We also need the pnext, the allocation size, device size, and the memory type index, which is what we get from the function that we just defined. Find memory type. Right? And we also have a bk free memory, which I'm gonna add already. Oops. bk allocate memory and bk free the memory. It's the counterpart for this one. Cannot fail. Takes also the device, the memory, and the allocator. if I manage to type this right. So back to our main. We need the S-type, the pnext is gonna be null as usual. The allocation size is gonna be the memory requirement size. And the memory type index, we use the function find memory type, passing in the physical device, which they are not passing here. The type filter is gonna be the mem requirements memory type bits. And the memory flags, they mentioned that we need to be host visible and host coherent. Format this and see what compiler errors do we get. Cannot find BK memory property host visible. Alright, so we just need to define these constants. BK memory property, grab all of these. Go to our bindings, top const, add it at the bottom. Record the macro for this. Tab const pk flags. Semicolon. There we go. I will check again. Expecting a type here because of type ascription. I think the problem is that I missed pnext pointer here. Now it's compiling. So in theory we managed to allocate some Vertex buffer memory. Can print it. Vertex memory. Vertex buffer memory. And go ahead and run this. Indeed, we get some memory. Next, we can bind the buffer memory to the Vertex buffer using this BK bind buffer memory. So we don't need that anymore. We can call BK bind buffer memory, passing the device, the Vertex buffer memory, and 0. I need to add this to the bindings as well. Okay, allocate memory. And after free, Find decay bind buffer memory. Right, the device size, the last parameter is the device size. The memory offset, sorry, as a device size. Most of the cases we will want 0 offset. This can fail, so return a decay result. What did I do wrong, or just that it's slow as hell? Okay. We saw that this function can fail, so let's not forget to check it. And we need to free the memory, of course. Destroy buffer. I think we should free the memory before destroying the buffer because it might be in use. So device, vertex, buffer, memory, and pointer null. Cargo check. We're okay. And filling the vertex buffer. I'm gonna do this section and I call it a string because I have to go. But let's try to do at least the filling of vertex buffer. So right after binding the bind buffer memory, we need to have a data pointer, a void pointer basically, and we need to map the memory for the device using this buffer memory that we just allocated at 0 buffer info. Ooh. This should be the same size that we used to create the buffer. So basically this. So let's yank it. Zero and data. Then we mem copy here, and after that we just map the memory. Device, vertex, buffer, memory. And that should be all. So basically we map the memory so that we have access from the CPU. Then we copy the contents of the vertex buffer, of the vertices array that we have defined, and then we unmap it. So let's go ahead and add these two functions to our bindings. Map memory and unmap memory. So up here, decay map memory, device, memory, decay device memory, offset, size, some flags, map flags, and we get a pointer to a pointer to the data. So mute, see, void, and this can fail, so be sure to return a picket result. And also the one for unmapped memory, which is much simpler, just takes the device and the memory that we map. And we just need to add the flags. And it compiled already, so I did not do anything wrong. Now we just need to do the mem copy. And how do we do that? How do we do mem copy? Do you have mem copy in Rust? We could use the one from libc. The mem module. Do you have something for copy? Copy. Pointer copy. Maybe. It isn't safe, but mem move. So what about this mem move? Do we have an example how they use it? Pointer copy. It has a bunch of unsafe warnings everywhere, but so if we do standard pointer copy, takes the source as first argument, so it should be our vertices as pointer, and then it takes the destination, I guess. Destination as a mutable pointer, so it should be data as mute pointer, or it's already a mute pointer, so, and then we take the size in bytes, I guess. Count? No, we take a count. So this should be vertices.len, I think. What do you not like? Expected struct phone row pointer. Can we just cast it? Does this work? It compiles at least. Maybe it doesn't work, but let's see. Let's see if we reach this point. vertex data copied. Cargo run. Let's see if we reach that point. Vertex data copied. Cool. We're so close, so let me try to finish this. I really need to go, but all that remains now is binding the vertex buffer during rendering operations. We're going to extend the record command buffer. So if we now go to bk command bind pipeline, we can, before we draw, we can also bind the vertex buffer. Command bind vertex buffers, command buffers, the command buffer we're using for the current frame, 0, 1 vertex buffer, by reference, and offsets, just a reference to 0, I guess. And here, down here, instead of hard coding the 3, now we can have vertices.len as u32. So we could potentially draw more than 3 vertices. Now we just need to add the definition for this command bind vertex buffers, add it in our bindings, bk command up here, okay, command bind vertex buffers, takes the command buffer, the first binding, that's what we set 0, the binding count, which was 1, oops, we need the types here, not the not the values. Binding count, pointer to the vertex buffers, and a pointer to offsets. The offsets const bk device size. Doesn't fail because it's a command. So check if this compiles, and it does. And the moment of truth, cargo run. Let's see, I will need to remove the panic, of course, the to-do that we had to do. Also get rid of this print. Run it one more time. And we are back to function parity. We can see the triangle. But now we are using the vertex buffer. So yeah, that's cool. So now we could change the color of the vertices, right? So where we define our vertices, if I can find it here, we could change the colors. Here they are saying change the first color only to be white. So here they change this to be white, and rerun the application, and we get the same result. So nice. Cool. So I think that was everything for today. We did a bunch of changes to support Vertex buffer. We did some changes in the shader. We created the vertex buffer, got the binding descriptions and attributes, and allocated memory for our vertex buffer, and modified the command buffer recording. Yeah, let's commit this, use vertex buffers instead of hard coding the vertices in the shader. Push this. And yeah, that was all for today. Thank you all for watching, and I will see you next time. Have a good day.